Welcome to an introduction to Chapter 4, and we'll divide this into two parts, and this is just going to be part 1 for today. And we're going to be talking about aqueous solutions, and in particular, we're going to be talking about the reactions that occur in the aqueous solutions. And so, the first thing you need to do is you need to be able to recognize an electrolyte, a weak electrolyte, so let's say strong electrolyte, a weak electrolyte, and a non-electrolyte. You'll need to know your strong acids, so you'll have to memorize those, and you will find that those are also strong electrolytes. And then weak electrolytes will be weak acids and also weak bases. And the way you recognize the weak bases is they contain a nitrogen and often a carbon. So the nitrogen's with the carbon. The way you recognize weak acids, they start with a hydrogen in their chemical formula, but they are not one of the strong acids that you memorize. And then a non-electrolyte is basically nonmetals, bonded to nonmetals. So this is going to be more of your organic compounds with carbon, hydrogen, nitrogen, oxygen, halogens, and you will not see a metal. Strong electrolytes will start with a metal. And so that ionizes in water, because when we talk about aqueous solutions, we're talking about in water. And water has this dipole, which is the hydrogens are slightly positive and the oxygens are slightly negative. And so it can orientate these different molecules like sodium chloride, where the sodium is oriented near the oxygen and the chloride is oriented near the delta positive hydrogens. So we're talking about aqueous solutions, so we are talking about water. And so metals are electropositive, and that means they give up an electron and become a positive charge. And in water solutions, they actually will break up and ionize. They become ions, right? So if you ionize, you become an ion, which is a cation, so that's the positive, and the anion, which is the negative. And so these separate, and electrolytes actually, strong electrolytes will conduct electricity. You can see that in your book. The weak electrolytes will just ionize partially. So you'll see these equilibrium arrows that go back and forth. And then a non-electrolyte will not ionize at all. So no positive, no negative. These are just covalently bonded compounds. All right, now, so once you do that, let's look at some checkpoint identifying electrolytes in our book. So, soluble ionic compounds. So now we're talking about precipitation. So you need to know your solubility guidelines. So those are on page 135 and 136. And you'll see that anything with a group 1, so your alkali metals, will always be soluble in water. And also included that is the ammonium cation. So these are all positives. What about the negative ones that are always soluble in water? So always soluble, and we'll put those in aqueous. That means they're soluble when we're writing precipitation reaction. Because I need you to be able to write precipitation reactions and predict which compounds are soluble, aqueous, and which ones are insoluble. So the anions that you need to know, So you have the polyatomic anion nitrate, you have acetate, and you have chlorate. And there's no exceptions. So anytime you see these, there's no exceptions. These are always soluble in water. So if you see those. And then you have chloride, bromide. These are your halogen, the negative ones. These are going to be soluble unless they're with these three: silver, lead, and mercury. And then compounds that have sulfate, which is your only 2- anion, are going to be soluble. So they're going to be aqueous unless you have these three, and then also 3 of the alkaline earth metals. So what are those? The barium, the calcium, and the strontium 2+. Now if you turn the page, you see these compounds that always need a trigger that they're insoluble. And so some insoluble compounds, so insoluble, so you want to write solid, they're going to precipitate out of a reaction, an aqueous reaction, are the carbonate, which is a 2+, the phosphate, which is a 3-, and the chromates, there's 4 of them, and the sulfide. So notice they all have higher charges, except, of course, if they're with these group 1, because these are always. So the exceptions are group 1 and the ammonium, because those are always soluble. Okay, and then we have to look at the hydroxide. The hydroxide would be included in this frequently insoluble compound. So those would be solid, unless, of course, you have group 1 here. But also we have to include one other one here, and that is barium. All right, so those are the precipitation solubility rules that you need to follow in order to write precipitation reactions. So now let's go back to the checkpoint in section 4.1 and see if we can answer those questions. So soluble ionic compounds. So they're always going to be, if they're soluble, they're always going to be strong electrolytes. So always strong electrolytes. What about soluble molecular compounds? Molecular. When you think about molecular compounds, you need to think about nonmetals. And these are going to be weak electrolytes. But I think the answer that they want here is sometimes these are going to be strong electrolytes. So sometimes they'll be strong electrolytes. Which of the following compounds is a weak electrolyte? All right, so let's look for a weak electrolyte. And remember, weak electrolytes are your weak acids and your weak bases. Well, lithium chloride, that would be a strong, because there's your metal. Weak electrolyte would be B, which is a weak base. Okay, so that's a weak base. You see it has a nitrogen and carbon, so that's a weak base, so that would be it. Potassium nitrate, and you know that potassium nitrate is always going to be soluble, and that's strong. It has a potassium. Sodium iodide, it's going to be strong. Sodium is a metal. And then nitric acid is one of the 7 strong acids, and a strong acid means it's going to be a strong electrolyte. Which of the following compounds is a strong electrolyte? Okay, so now the next question, we have hydrofluoric acid, and it's not one of the 7, and it starts with a H, hydrogen. So this is a weak acid, and we know that weak acids are also weak electrolytes. And then we also have H2CO3, and that would also be a weak electrolyte. And that compound is a weak acid. Sodium fluoride, you know that's strong, right? So sodium fluoride, that's going to be a strong one because the sodium. NH3 is going to be weak. This is a weak base, ammonia. So it's going to be a weak electrolyte. And then water is not electrolyte. Water is just a molecular compound, and it's actually the liquid itself. So it doesn't conduct electricity. All right, so now let's go on and write one of the objectives you need to be able to do is to write ionic equations and net ionic equations. So let's write ionic equations and net ionic equations. So going to the checkpoint, I'm on 4.2.1. Which of the following are water soluble? So water soluble means you put them in aqueous. Okay, so sodium sulfide. Well, what's our rule? Sulfide is insoluble unless group 1. Unless group number 1. So since it's group 1, that's going to be aqueous. And I will make that a blue. So that would be water soluble. That's water soluble. Okay, we have barium, C2H3O22. This is that acetate, and there's no exceptions here. So this one's going to be always soluble. So we can do aqueous here. Calcium carbonate. Well, carbonate is one of those that are typically insoluble unless it's with group 1 and or ammonia. So calcium, that's going to make this a solid. So that's going to precipitate out. Copper bromide. Well, bromide is typically soluble unless it's with the 3. Remember the 3? Unless it's with mercury, lead, or silver. So this would be aqueous. All right. And also group 1, right? But it's also soluble. Okay, and then what we got? We got mercury chloride. Okay, and then that's going to be solid because we just said that these halogens, bromine, chlorine, and iodide, are soluble unless they're with one of these 3, and there's mercury. Which of the following are water insoluble? So water insoluble would be a solid in parentheses. And so we have silver, chromate, and we learned that chromate is typically insoluble unless it's with group number 1 and ammonium. So this is definitely going to be a solid. So that would be water insoluble. We have lithium carbonate. Lithium is group 1, so you don't have to look any further. Group number 1, lithium, group number 1. It's going to be aqueous, so that's soluble. We have calcium phosphate, and you know phosphate is typically insoluble unless it's with group 1 or the ammonium. So here it's going to be a solid. Barium sulfate. Sulfate is typically soluble unless it is what? With silver, mercury, lead, and then the other 3, right? Calcium, strontium, or barium. And so here's with barium, so that's going to be a solid and it's going to be insoluble. And then we have zinc chloride, and we know that chloride is typically aqueous, soluble, unless it's with group 1, and zinc is not group 1, so that would be aqueous. So the question is, which of the following are water insoluble? And those are our answers. All right, so let's go to the next one. What are the spectator ions in the ionic equation for the combination of lithium carbonate and barium hydroxide? So let's write our reaction here. We have lithium carbonate, aqueous, plus barium hydroxide, aqueous. Now, so if we want to write our ionic equation, we got to do 2 lithium plus, so we're going to separate these in our ions. So we want to do first, so we have different charges. Barium 2 plus 2 OH minus. We don't need parentheses there. All right, so to predict the products, I want to match the lithium with the hydroxide, and I want to mix the barium with the carbonate. And then when I mix these, I have to decide when lithium hydroxide comes together, so that would be LiOH, and it would just actually be 1, right? So when they come together, is that soluble or not? So when we bring these together, we have to make the decision what goes into the parentheses. And then when we bring barium carbonate together, we have to decide whether it's going to be aqueous or solid on the product. So this is the predicting the products, the next step. So the first thing you want to do is break these into the ions. So step 1, break your reactants into ions. And then step 2, you want to, I'm going to say do-si-do. So we switch partners because we're predicting the product. So when you predict the product, you have to figure out when these come together. So we know sodium or lithium is always going to be what? Aqueous. So anytime you see a group 1, you can just go right aqueous. Now here, carbonate is one of those that typically are insoluble, right? Carbonate is typically, what's the so we got to apply our solubility rules. And unless it's with group 1. So that would be solid. So we can put a solid there. So when we predict the products, anything that's aqueous is going to stay in its ion form. And then, so we can just copy that here. And then the barium carbonate is going to be a solid. So we keep that together. Now, spectator ions. What are the spectator ions? That's the actual question. So spectator ions are going to be on the same side. So you can see we have lithium and the hydroxide, and they cancel out. So the answer for that would be the lithium and the hydroxide. And so the answer would be B. And then, but we're just going to go ahead and take it to the next step and go ahead and write our net ionic equation, which would be, you use these two here that come together to make your solid. So you see I've highlighted these, and when I write my net ionic equation, I would write barium 2 plus aqueous plus the carbonate aqueous comes together to form barium carbonate solid. And that's my net ionic equation because the spectator ions have been crossed out. Okay, let's go to the next one. All right, so the last thing we need to do is oxidation reduction reactions. So what I want you to be able to do is I want you to be able to assign oxidation states to the elements. And this is in a compound and also in an element. Okay, so we need to do that to both of them. And the other thing I need you to be able to do is in a reaction, we call it a redox reaction, I want you to figure out which reactant, so it's on the left side, is oxidized and which one is reduced. Now keep in mind, if it's oxidized, it is the reducing agent. And if it's reduced, it's the oxidizing agent. These are kind of bizarro world. So I always draw my, I don't know if you've seen this before, but this is Leo. Okay, Leo. Leo is a lion. I can draw my lion here. Okay, so Leo is a lion, and Leo says grrr. Okay, so Leo is the loss of electrons is oxidation. And so you're going to see that as an increase in oxidation state. Okay, so the oxidation number will increase. Grr is a gain in electrons, and that's reduction. And so that's a decrease in the oxidation state, and that will be oxidation. So you kind of have to remember that. And then when you see the reactions, there's some rules on oxidation numbers that I recommend that you read. An oxidation in any element, so some of the rules that in any element, the oxidation state is 0. Oxidation numbers don't really exist. We just give them numbers and apply these rules in order to make sense of it in our own world. Oxidation numbers in a chemical species, so in a compound, the overall charge is 0. You've already been doing this in order to do nomenclature. Oxidation states of fluorine, so there's a table, 4.5. And so fluorine is always a -1. There's no exceptions. Group 1A and 2A is +1 or +2. There's no exceptions to that. Oxygen's 2-, except for a few situations which you're not going to see. And then group 7A is 1-, which is with fluorine. And there are a few exceptions in that, but you don't have to worry about the exceptions on that. You do have to worry about exceptions on precipitation reactions. So let's work the example assigning oxidation states to elements and compounds. So let's work the example that the book has for you. So you have potassium permanganate. I really like how they do this. They do these little circles here. And this is your oxidation number. And then this box is total contribution to charge. Okay, so when you apply these rules, so oxygen is always 2 minus, so you can do -2 for oxygen, that's the oxidation number. Potassium is in group 1, so that's a +1. And you see how there's 4 oxygens? So 4 times -2 is -8. So the overall charge, contribution of charge is a -8. There's only 1 potassium, so 1 times +1 is 1. Now, the contribution of the charge, the compound has to overall charge up to 0 because there's no charge on this compound. So if you have a -8 and a +7, then you need a +7 charge for this to equal 0. And so there's only 1 manganese, so the answer for that 1 manganese oxidation state is a +7. And you have more examples of those. Let's see if we can go to your checkpoint. Okay, so let's do 4.411. So problem 4.41. Determine the oxidation number in sulfur for each of the following species. So we have H2S, we have SO3 minus, we have SCl2, and we have S8. And I like how they did this, so I'm going to put the little oxidation state for each one of those elements. And then I'll put the boxes for the overall charge. Now, before we go any further, this is an element. It's by itself. It's only one capital letter, so that one's going to be 0. Elements are always 0. Okay, so they take on charges when they bind, right, by ionic bonding in a compound. Okay, so hydrogen is always going to be +1. And so how many are there? There's 2. So 2 times +1 is +2. So that means the sulfur, the overall charge, needs to be a -2, and there's only 1, so -2. So that one's a -2. Let's go to the next problem. Okay, we said that hydrogen is a +1, and so there's only 1, so +1. Oxygen is always going to be a -2, and there's 3 of them. So what's 3 times -2? -6. So that's -6. Now the overall charge is negative. So the overall charge is -1, and you have a -6, and you have a +1. So what charge do you need? A positive charge do you need for this sulfur? So this needs to be a +4. Is that right? So 4 + 1 is +5, and a -6 equals a -1. So we need +4. There's only one of them, so +4 is the answer for that compound, for that element. All right, so let's go to the next one. We said that the chlorine is a -1. There's 2 of them, so 2 times -1 is -2. And so now we need a +2, and there's only 1, so there's a +2 there. And then we also said that in an element it's 0. So if we look at our answers here, what do we see? We see a -2, a +4, a +2, and a 0, which is answer E. And if I look at the back of the book, that is correct. So I like that way of doing it. Okay, the next questions, we need to be able to identify the reducing agent. So now let's look at reactions. So you have magnesium, which is a solid, and you react it with HCl, and you get magnesium, chloride, and hydrogen. Now, how do you recognize redox reactions as compared to neutralization reactions? Well, neutralization reactions, you have acids and bases. And when you memorize your strong acids, because that's the only ones you're going to have in Gen Chem, that's a neutralization reaction. And it always makes a salt, which is a plus and a minus, plus a water. And your net ionic equation is always going to be the H plus the OH minus goes to water. Okay, so hopefully you understand that. Okay, what about precipitation reactions? Okay, so precipitation reaction, you have a compound that's aqueous plus another compound that's aqueous. And so you break them into your ions, and then you do your do-si-do. Do-si-do. And then you predict your products as whether they're aqueous or solid. Now here, when I recognize redox, I always see that's an element plus a compound. And then on the product side, you see a compound plus an element. And it actually kind of exchanges that element. So we know this is redox as you have an element here and you have a compound. And when I see that, I think of redox. There are like 3 different redox types of reactions that your book talks about. Now, we have to assign oxidation. That's what you do. You assign oxidation states to these elements and just like we were doing. So an element is a 0. And then over here, it's going to be a 0 because hydrogen is an element. So it gets an oxidation state of 0. When elements are in compounds, they take charges, right? Because they give up electrons or they gain electrons. So here, the hydrogen, and what do we say about hydrogen? In a compound, it's going to be a +1. And so then chlorine is a -1. And then over here for magnesium, magnesium is a +2, and then chlorine is still a -1. So even though there's 2 of them, it gets a -1. So you notice that chlorine stayed the same. Okay, -1 on the reactant side, -1. So no change. So nothing happened with it. Now what about magnesium? It went from 0 to a +2. So it had an increase in the oxidation number. And what do we say? Increase is oxidation. And then we look at the next one, hydrogen. And I just match them up over here on the top. We will go from a +1 to a 0. I think of my bank account. And when I go from $1 to 0, I know that's reduction. So HCl, the hydrogen's being reduced, and the magnesium is being oxidized. You can't have one without the other. Now, you also need to be able to answer the question, if something's oxidized, it is the reducing agent because it's actually doing the reducing. And if it's reduction, then it's the oxidizing agent. It's the one that's doing the oxidizing. So I do this and then I answer the question. What species is the reducing agent? Okay, well here I wrote it down. Reducing agent. And then I go over to the reactant side and I say magnesium. So I see that it is A. And then I check my answer and it is A. Okay, so magnesium solid is A. Which of the following equations represent a redox reaction? So we're looking at 4.43, and this is just, can you recognize a redox equation? So in the first one you have magnesium plus oxygen going to magnesium oxide. And so did you get a change of oxidation states? 0 and 0. Here, we'll do that. And then over here, you got a +2 and a -2. So you see that you have magnesium undergoing oxidation because you had an increase in number, and you see oxidation reduction for oxygen. So that would definitely be a redox. Okay, what about the next one? You have copper plus platinum chloride, and you got it going to copper chloride plus platinum. And I see we have an element by itself. So I say, okay, that's a 0. Over here it's a +1. Nope, +2, isn't it? +2. Platinum here is a +2, and over here it's a 0. So platinum is being reduced, and copper is being oxidized. So that's a redox reaction. And then the next one, C, is ammonium chloride plus silver nitrate. And I see that those are both aqueous solutions, and that's going to be a precipitation reaction. I do not see an element. The next one, we have sodium azide, which sodium azide, folks, is the active ingredient in your airbags. So if you were ever in a car accident, your airbag went off, it's the sodium nitride that actually detonated, because it can detonate upon mechanical force, to give nitrogen gas. And that nitrogen, that's the equation we're doing right here, nitrogen gas. And it's the nitrogen gas that fills up your airbag. And so you can see when it's in a compound, sodium's a +1, and the azide is actually a covalent compound that looks like this. And this is organic chemistry, so that's a -1. It's a polyatomic, right? And then over here, it's by itself, so it's a 0 and it's a 0. So you can see sodium is being reduced, and the azide is going from -1 to 0, so it's being that reduced as well. What am I missing? -1 to 0 is oxidized. Yeah, so if I have -$1, I'm in debt, and I go to 0, that's moving forward, so oxidized. So yes, that would be a reduction oxidation reaction. And then the next one is decomposition. Calcium carbonate, and it's going to calcium oxide plus carbon dioxide gas. And let's see if we have an oxidation state. We have a compound, so this is +2, and this is -2. But we really have to break each one of these down. So this one is -2 for oxygen in a compound, and there's -6 there. So this carbon would be +4. And then we come over here to calcium, and it's +2. Oxygen is -2 here, and then +2. So this is not. So this stays the same, +4. And then this is a -2. So there's no change in oxidation state, so not a redox. And if we go and check our answers, we see that A is redox, B is redox, and D is redox. So we're correct on that. You can look at the activity series. I think it's interesting, and which of the following redox reactions will occur, and you can figure that out and do that. I'm not going to have you memorize that activity sheet, the series, and it is interesting, though, in the activity series, there's a list of metals from top to bottom, and you have to have metals listed at the top of the activity series are called active metals, and they include the alkaline earth metals, and these are so reactive that they're not even found in metal, and then they will actually will be oxidized. So what's interesting, I think, about this activity series is gold is considered very valuable. Okay, I'll write gold. And gold is the least oxidizable metal. And so it's it's at the very bottom of that series. You will be doing a lot of redox reactions in Gen Chem 2. So this is as much as we're going to touch on it for Gen Chem 1. I will stop there. We're going to talk about concentration of solutions section 4.5, and I will introduce molarity. I know that you have a lab practical on that, so we'll do that after the exam, and we'll also do dilutions and stuff like that. So we will touch on this before we go to the next chapter, and I'll do a part 2.